Before we continue, let's take a quick recap on what we have been doing in the last 3 videos. We have seen in part A that the Bohr model of the atom is true if and only if the planetary model of the atom is correct. By making this proof, we discovered that Planck's constant, which so far has been referred to as a fundamental constant of nature, is not a fundamental constant. It is a function of different constants, which are the Coulomb's constant, the mass and charge of the electron, and the Bohr radius. This was a summary of the more detailed video titled Planck's constants of the cosmos, which modifies the Bohr equation in a way that can describe all elements. Following from that, we also saw that gravitational waves can be emitted and absorbed by solar systems according to the equation E = gf, in the same way that EM waves can be emitted and absorbed by atoms. According to the wave-particle duality, we established that the graviton is a particle of the gravitational wave in the same way that the photon is a particle of EM waves. The underlying problem of acceleration of an orbiting electron spiraling into the nucleus to annihilate the atom, which caused the planetary model of the atom to be abandoned, was solved in the last video. It was demonstrated that the planetary model of the atom is the correct model, and that quantum mechanics was wrong. For more proof of the incorrectness of quantum mechanics, refer to my other playlist titled Quantum Gravity, where you will be presented with the Schrödinger equation of the cosmos. Today, we will be proving that charge curves space-time in the same way that mass curves space-time, and explain why light was a good candidate for detecting gravitational waves. The knowledge of the existence of charges has been around long before Isaac Newton wrote down his formula for the gravitational attraction between two masses. However, there was no working mathematics to quantify these charges and the force they exert on each other. There was suspicion that this force varies according to the inverse square law, just like Newton's gravitational force. Nevertheless, it was not until 1785 that a French physicist by the name Charles-Augustin de Coulomb did an experiment that finally led to the mathematical equation we call Coulomb's law today. He used a torsion balance to study the repulsion and attraction forces for charged particles and determined that the magnitude of the electric force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. The torsion balance consists of a bar suspended from its middle by a thin fiber. The fiber acts as a very weak torsion spring. In Coulomb's experiment, the torsion balance was an insulating rod with a metal-coated ball attached to one end, suspended by a silk thread. The ball was charged with a known charge of static electricity, and a second charged ball of the same polarity was brought near it. The two charged balls repelled one another, twisting the fiber through a certain angle, which could be read from a scale on the instrument. By knowing how much force it took to twist the fiber through a given angle, Coulomb was able to calculate the force between the balls and derive his inverse square proportionality law. Unlike other forces that we are familiar with, where two or more bodies have to be physically touching one another in order for the force to act, the Coulomb's force was actually an action at a distance force. That is, the bodies experiencing the force do not necessarily need to be in physical contact in order for the force to act, just like gravity. Unlike the Coulomb's force that can be both attractive and repulsive, the gravitational force is only attractive, at least so it was thought. It is a result of mass and also acts at a distance between two massive objects. It was Isaac Newton that first came out with the quantitative way of looking at this force. He stated that the magnitude of the force between 2 point masses is directly proportional to the multiple of their masses and inversely proportional to the square of their separation. Like Coulomb's force, this force obeys the inverse square law. Its formula was also empirically determined by a method that Newton called inductive reasoning. We all know the legend of how Newton was inspired by an apple falling over his head when he was probably taking a selfie, to ask the question, if the apple could fall towards the earth, does the moon also fall towards the earth? Imagine the Earth-Moon system as follows. Let the distance from the center of mass of the Earth to the center of mass of the Moon be little r. Let's map out a circle around the Earth, centered at the center of mass of the Earth, that passes through the center of mass of the Moon. The radius of the circle is thus equal to r. Like the apple in Newton's thought, the Earth is applying a force on the Moon, and the Moon is also applying a force on the Earth of the same magnitude according to Newton's third law of motion. But because the Earth is way heavier than the Moon, and thus have more inertia, the smaller Moon will have to move towards the center of the Earth just like the apple. However, the Moon doesn't fall to the center of the Earth like the apple, because the Moon is moving while the apple was not. But to cause an object to move, you must apply a force according to Newton's first law of motion, F equals ma, which is also known as the law of inertia. So, how can we apply the force on this Moon so that it moves as we observe in the solar system? Let's assume we want the motion to be anticlockwise. So let's try applying a force on the Moon like so, which points into the circle. We can include a coordinate system at the point of action of the force, like so. If we resolve this force with respect to this coordinate system, we have the following components. We see that one of the components of the applied force points towards the Earth's center, while the other points in the direction of the linear velocity of the Moon. As a result, the Moon will spiral into the Earth following this trajectory. So we see that the direction of application of this external force is not appropriate to produce circular motion. Now, if we apply the force such that it points away from the circle, like so, we can resolve it into its components as follows. This component of the force F subscript v goes to accelerate the object from rest to its final velocity v, which is maintained throughout, while the other component has to be such that it balances with the gravitational attraction so that the Moon doesn't spiral in like in the first case. So we have F subscript r equal to gmm over r squared. This equation must hold in order for the Moon to stay in orbit. These balance forces pull on the Moon and stretches it. A clear example of this is the shape of the Earth, which is stretched out at the equator. This force that balances the centripetal force is what we call the centrifugal force, and it must be present for any kind of circular motion to occur. If the force was applied for a certain amount of time, little t, then according to this equation, the velocity attained by the moon is given by Ft on m, since it starts from rest. If there is no friction or viscous drag, which is the case with empty space, the moon will continue with this velocity according to the coordinate system used forever, according to Newton's law of inertia, which states that a body at rest will stay at rest forever, and a body in motion will continue to move at constant velocity until an external force acts on it. An obvious question is, where did this external force come from? The answer is simple. It came from the chaotic movement of the dust and particles that combined to form the solar system. Remember, during solar system formation, there is a lot of energy present that acts in all directions. So, the answer to Newton's question is no. The moon does not fall, but his formula was correct. This was the leading theory of gravity for hundreds of years, and no one dared to challenge the great Isaac Newton until Einstein. Einstein was not happy with the idea of action at a distance, that a body is able to affect another body without touching it. So he wrote a different equation for gravity, which is the Einstein's field equation, where he described gravity as the curvature of space-time around a massive object caused by the massive object. These terms on the left describe the curvature of space-time by matter, and this term on the right describes the amount of matter present in that given space. It is called the stress-energy-momentum tensor, and it shall be our point of focus. Let's go ahead and derive it. For a mass capital M in space, there is a corresponding gravitational potential phi. The force that this mass will exert on a unit mass in the region of the potential is given by minus the spatial derivative of phi. In 3 dimensions, it is equal to minus nabla phi, where nabla is the sum of the derivatives along the different axes x, y, and z. According to Newton's law, this force is equal to minus gmm on r squared. But we are dealing with a unit test mass, so little m is equal to 1. The force becomes minus gm on r squared. The minus indicates that the force is attractive. Remember, this is the same force that we can call the centrifugal force. And in that case, to compute the magnitude of the centrifugal force, we would not need to include the minus sign, which means the force will be positive. So this can be looked upon as an example of positive gravity. What we want to find is the total force in the entire area round the mass where a test mass will experience a force. So we integrate over the area as shown. Since this area is a sphere, this integral becomes this. The r squared cancels and we have this. So the integral of f dot a is equal to minus 4 pi gm. We can express the mass as a function of the mass density ρ to have this. There is a mathematical theorem called the divergence theorem, which says that integrating the force over a closed area is the same as integrating the gradient of the force over the volume bounded by the area. So we can now write our equation so that we have the integral over volume on both sides, like so. For this to be equal, then the gradient of F must be equal to minus 4 pi g times rho. But F is equal to minus the gradient of the potential. So putting this here, we get the Laplacian of the potential equal to 4 pi g rho. There is a term called the conical delta, capital gamma, giving us a function of the metric tensor g0 This term has units of force and is therefore attributed to force. Therefore, by our definition of force, this simplifies to the metric tensor equal to 2 phi plus a constant of integration. So phi is equal to this. The Laplacian of this gives 1/2 the Laplacian of the metric tensor. Therefore, our equation becomes this. We need this to be a tensor because the left-hand side is a tensor. So we have to convert the mass density into the stress energy momentum tensor using the momentum force vector in special relativity. You can check that out to see how it is done, but for the purpose of this video, we shall just write this out as 8 pi g times the tensor over the speed of light raised to the power 4. And this is how the right-hand side of Einstein's field equation is derived. I have made this derivation because I want to use it to illustrate something about charge. Einstein did all this to eradicate the idea of action at a distance force, which he succeeded to do for gravity. But gravity acts in the same way that the Coulomb's force acts, which is also an action at a distance force. So there also has to be a general relativity explanation of how two charged spheres in space exert a force on one another without touching. Let's quickly rush through the steps for a charged body in space. Now, the force it will exert on a unit test charge in its vicinity is minus the gradient of the electric potential phi. This force is equal to kq over r squared. And by the same process, we find out the integral of f dot dA is equal to minus 4 pi kq. We can express the charge in form of the charge volume density as follows. Applying the divergence theorem in the same way as before, we get the Laplacian of phi equal to 4 pi k rho. The conical delta is a force term, so we can also associate it with electrostatic force in the same way we associated it with gravitational force. And when we do that, we end up with the same equation, with G simply replaced by K, the Coulomb's constant. This indicates that charge curves spacetime exactly as mass does. Since charge can both be positive and negative, there can therefore be positive and negative curvatures of spacetime. If you have watched all the videos on the playlist Quantum Gravity, and on these playlists Particles and Waves, you will have noticed that all the equations related to mass are identical to those related to charge, as if mass and charge are the same thing. And it is our definition that have made them to seem different. In my opinion, I think they are the same. For those of you interested in a form of Einstein's equation that can allow time travel to the past by curving space-time the opposite way, you've got it. It is the Einstein's field equation with charge. To me, time travel, like quantum mechanics, is one of the things that are interpreted in an incorrect way. I shall do a video on the idea of time and time travel in future videos. So now we have seen that charge can curve space-time just like mass, and they obey the same equation. Therefore, an accelerating charge will produce a wobble in space-time that will spread as a wave, just like accelerating masses produce a wobble. This shows that the kind of waves produced by accelerating charges is the same as those produced by accelerating masses, just like we have seen in part A, B, and C of this series. Maxwell's equations tell us that also. These waves are called EM waves when they are produced by charges, and are called gravitational or GM waves when they are produced by masses. Since they are the same kind of waves, we can therefore safely say that gravitational waves are EM waves. As a consequence of this, they should also be able to be described by Maxwell's equations. That will constitute a video on its own. This new knowledge is also going to help us explain unequivocally the so-called electron leap and many other things. Waves in the same medium can pass through each other undisturbed, such as waves on the surface of water or waves on a string, especially if they are of different frequencies. GM and EM waves are both waves in the same space-time medium, and therefore can pass through each other undisturbed. This is why, even though gravitational waves distort the position and shape of everything in its path, they cannot distort light or any other EM wave. This is why light is the appropriate thing to use in the gravitational waves detector. I hope I have managed to convince you that mass and charge can obey the same Einstein equation. You can do the math yourself to convince yourself that this is true. And you can make solutions of the Einstein's equations for charge and see whether they can produce results that are consistent with what is observed today. So I hope I have convinced you that mass and charge could be the same thing, and we are going to find out by looking at more examples. So I hope I see you next time. If you are new to this channel, please subscribe and click on the notification icon to get notified each time new videos are uploaded. If you have already subscribed, please turn on the notification bell if you haven't done so. If you enjoyed the video, please enable to give it a thumbs